Hi, this lesson is on applied optimization problems. So we're going to use calculus to determine values that would optimize particular values that you're looking for. And optimizing means maximizing or minimizing. We'll be using the first or second derivative tests in order to determine if the values you find are maximum or minimum values. So some general steps that you'd want to consider for these problems is to draw a picture if it's applicable. And a lot of times these will be geometric in nature, so a picture will make sense. You're going to want to identify the formula or formulas needed. And so usually you'll have two formulas because you'll have something called a constraint formula. And so a constraint will be something that defines some sort of limitation to what you are trying to determine. And the other formula would be the formula associated with the variable that you want to maximize or minimize. In some cases, you're going to want to substitute where possible so that you're only working with one equation with one variable in the one that you're taking the derivative of to maximize or minimize. You're going to use the first derivative, set it equal to 0 and solve it to find critical values. And then we're going to use one of our tests to determine if those values are maximum or minimum in order to prove what you're looking for. All right, so most of these problems will be geometric in nature, but there's a lot of examples, particularly in business, where optimization is very practical, but these will all be more geometric in nature. So first example says find two positive numbers whose product is 100 and whose sum is a minimum. Okay, so we're trying to find these two positive numbers. Our constraint is that the product x times y is equal to 100. And we are asked to minimize the sum of those two numbers. So we want to minimize s equal to x plus y. So always make sure that you're coming up with an equation for what it is that you want to minimize. So, you come up with the variables that are appropriate and then move from there. So before we take the derivative, you're going to want to use your constraint and solve for one of the variables. So here I solved for y. You could have also solved for x. Either one would work. And we use that equation y equals 100 over x and substitute it into your s equation. So I have s equals x plus 100 over x. So now I have one equation in terms of just the variable x. So on the next line, I rewrote 100 over x as x to the negative 1 to make it easier to take the derivative of. All right, so now we take the derivative and we set equal to 0. So s prime is 1 minus 100 x to the negative 2 equals 0. So I'm going to move the 100x to the negative 2 over to the right side and rewrite it as a proportion. So I have 1 equals 100 over x squared. Cross multiply, you get that x squared is equal to 100. Now normally you would say then x is equal to plus or minus 10, but remember the original problem said that we're looking for a positive number. So you really only need to say x equals 10. And when x equals 10, you're going to want to know what the y value is. And so remember, we said up here that y equals 100 over x. So y is equal to 100 over 10, which is also 10. So we have our two positive numbers that we're looking for. But now we have to make sure that we prove that it is a minimum. And so we're going to use our second derivative in order to determine that. So remember, the second derivative tells you that a function is concave up when the second derivative is positive, and a function is concave down when the second derivative is negative. All right, so let's see. I take s double prime. So I have s double prime is equal to 200 x to the negative 3. And now I want to find out what is my value of s double prime at x equal to 10. So you plug that in here. And at 200 over 10 to the third power, well, that is definitely a positive number. Remember, positive concavity means that your function is concave up. And if something is concave up, that means you have a minimum, which is exactly what you were looking for. So the two positive numbers, 10, x and y are equal to the same number. That will give you a product of 100, but a sum that is minimized. Okay, so we want to now find the dimensions of a rectangle with a perimeter of 100, whose area is as large as possible. So I'm going to just change the color here. This is a rectangle, so I draw a picture here. I'm going to use x and y for my variables. My constraint is this statement here. The perimeter is 100, so I have that here. 2x plus 2y equals 100. And then what I'm being asked to maximize, because area is as large as possible, that means it's a maximum problem. You want to maximize a equal to x times y. So just like in the previous example, I want to eliminate one of the variables here in the equation that I need to take the derivative of. So I go back to my constraint and I solve it for y. So you have y is equal to 50 minus x, and that 50 minus x gets substituted right in here. So I'm left with a is equal to x times 50 minus x. So before we take the derivative, it would make it easier to take the derivative if you were to distribute first. So I get my area is equal to 50x minus x squared. So now I take the derivative. So I get 50 minus 2x equals 0. Solve that equation and you get that x is equal to 25. And just like we did in the previous example, we also have to find the value of y. Remember, y is equal to 50 minus x, so it's 50 minus 25. So we get that x and y are both 25. So that means that, in fact, our rectangle is a square, and that's okay. A square is a special type of rectangle. Okay, but just like the last example, we need to prove that the dimensions of x equal to 25 and y equal to 25 actually maximize the area of that rectangle, which we now see looks like it's a square. So again, I'll use the second derivative. So remember, the first derivative was 50 minus 2x. Therefore, the second derivative is just a constant of negative 2. So that means it's always negative, which means it's always concave down. Concave down looks like this, which means that you have a maximum at your critical point. So that proves that your area is maximized given the constraint of the perimeter equal to 100. Okay, here's another one. It says that, again, let me change the color so it's easier to follow. It says that a farmer has 2,400 feet of fencing and wants to fence off a rectangular field that borders a straight river. He needs no fence along the river. What are the dimensions of the field that has the largest area? Okay, so here's my picture. So I need a fence along 3 sides of this rectangular field. So the 3 sides are labeled X for the horizontal side and Y on the 2 vertical sides. And here's my river just below, right? You can put the river on any side you want. I just happen to put it on the bottom. So what that means is that my fencing only goes along 3 sides. So my constraint is X plus 2Y equals 2,400. Remember, no fencing along the river, so you wouldn't put 2x the way we normally would with a perimeter problem. So what we're being asked to optimize is we want to maximize the area. So again, here's your area formula. A is equal to x times y. And again, I need to eliminate one of the variables. So this time I'm going to solve the constraint for x. Again, you can choose any variable you want. So I solved for x, and I get x is equal to 2,400 minus 2y. That gets substituted in here in my area formula. All right, so again, before I take the derivative, I'm going to distribute. So I have that the area is equal to 2,400y minus 2y squared. So now we're ready to take the derivative. You just have to use power rule. So a prime is 2,400 minus 4y. And remember, set the first derivative equal to 0 to find critical points, which are your potential extrema. So you get 2,400 equals 4y, divide by 4, y is equal to 600 feet. Okay, but we need dimensions, which means I need the x and y values. So I know that y is equal to 600. Remember, x was defined to be 2,400 minus 2y. So x is equal to 2,400 minus 2 times 600. That's 2,400 minus 1,200. So you get that x is 1,200. So now again, we have to prove that these are dimensions that will maximize the area of the field. So again, I take my second derivative. Second derivative, a double prime is -4. This is also always less than 0, which means it's concave down, and concave down means that my critical point represents a maximum. Okay. So let's go on. You want to find the point on the parabola y squared equals 2x that is closest, sorry for that typo, closest to the point 1, 4. So 1, 4 is not on the parabola, so it's beyond that. It's outside of it actually. So if I were to draw a picture just to help you visualize it, y squared equals 2x looks something like this, and 1, 4 is, well, it's about here somewhere, okay? So we want to find the point on this parabola where the distance from 1, 4 to the parabola is minimized. So we're going to use the distance formula. That's how you calculate the distance between 2 points. And so as a reminder, distance formula is right here. Similar to our other problems, we do have a constraint. The constraint is the equation itself. So y squared equals 2x. So again, you can solve for y or you can solve for x, but I would probably avoid solving for y, because if you do solve for y, you're going to end up with the square root of 2x. And then you'd have to work with a radical, and that just gives you a little bit more work to do in terms of derivatives. So I'm actually going to solve for x instead. So I have x equals y squared over 2, and that's the value that you substitute into the distance formula in order to just work with one variable. So my equation is going to be in terms of y and not in terms of x. So here's my substitution. I have d is equal to the square root of, so my x becomes y squared over 2, and the other x value, well, that comes from here, from the point. So I have y squared over 2 minus 1 squared plus, then the y value, well, that's just y, and then minus 4, and again, that comes from the coordinate. So this is an important fact that you're going to want to remember for future math classes, that if I optimize the distance formula, or d equal to the square root of this expression, the answer I get is the same as the answer that I would get if I squared both sides. And by squaring both sides, well, that again saves quite a bit of work in terms of finding a derivative. You're basically avoiding like one layer of chain rule. So I'm going to square both sides, and just for practical reasons, when I square d, I get d squared. I'm going to call that a function of y, which you see here, and then the square root goes away on the right side. So now I have f of y equals, So the expression that you see to the right of f of y here is basically just the two binomials above squared. So when you square the first binomial, you get 1/4 y to the fourth minus y squared plus 1. And when you square the second binomial, you get y squared minus 8y plus 16. All right, so there are some like terms. So we combine like terms in this line. I have 1/4 y to the fourth minus 8y because the y squareds, well, they cancel each other out. And 1 plus 16 is 17. So that's the equation you want to take the derivative of. And so power rule, f prime of y is y cubed minus 8 equals 0. So if you solve this, take the y cubed equals 8, take the cube root, you get that y is equal to 2. And when y is equal to 2, well, remember, x is y squared over 2, so that's 2 squared over 2, which is also 2, which you see right here. So that's the point that we are assuming is on the graph that is closest to 1, 4. And remember, this graph that I drew here on the left is not super accurate. It was just kind of thrown together, but it looks like a pretty good guess that my 0.22 is probably the closest point to 1, 4, but we have to prove it. And again, we're going to use one of our derivative rules. So we want to prove that y equal to 2 on the graph of y squared equal to 2x minimizes the distance to the point 1, 4. So this time I'm going to use the first derivative test. And again, it doesn't matter which one you use. I just want to show you that you can use either one. If I plug in here into my first derivative, pick something less than 2, like let's say 1, plug that in, you get a negative result, and a negative result means that the graph is decreasing before 2. And if I pick something greater than 2, like 3, and plug it into your first derivative, well, you get a positive result. And so again, when you see a change in sign from negative to positive, before and after the critical point, that's considered to be a minimum value. And so therefore, the 0.22 minimizes the distance to the 0.14. All right. Let's move on. So this time I have a box. So I have 1,200 centimeters squared of material available to make a box with a square base and an open top, and we want to find the largest possible volume. So again, a picture is really helpful. So remember, the base of the box is a square, so that means 2 of my dimensions are the same. Okay, let me change the color so it's easier for you to follow what I'm doing. Okay, so the base is a square, so I have 2 dimensions that are the same, but you're not told that the height of the box is the same, so I'm calling it y. So all of the panels that make up the box is what makes up this constraint value of 1,200. So my constraint formula is the sum of all of the areas of the 5 rectangles or square, because the bottom is a square, that make up the box. Remember that the top is open. So the bottom area is this bottom one here. And so that's the x squared part. The sides, the 4 sides that go around the box, well, those have dimensions of x and y. So it's xy 4 times. So that's why I have xy plus xy plus xy plus xy. Well, we write that as 4xy. And the sum of those areas is 1,200. So that's our constraint formula right here. You're being asked to maximize volume. So Remember, volume is length times width times height, but our base is the same dimension, so it's just x times y, which is x squared y. So again, I need to eliminate one of the variables, so I'm going to eliminate y from my, I'm going to solve for y in my constraint formula and then plug it in. Okay, so when you do that, I'm going to subtract x squared from both sides, I'm here, and divide by 4x, I'm here. And when you simplify, you get that y is equal to 300 over x minus 1/4 x. So that's the value that you plug into your volume formula. So I get x squared times 300 over x minus 1/4 x. So simplifying gives you 300x minus 1/4 x cubed. We set that equal to 0. We take the derivative and set it equal to 0. So we get 300 minus 3/4 x squared equals 0. Add 3/4 x squared to both sides. Multiply by 4/3 to get rid of the fraction. And so you get x squared equals 400. When you take the square root, remember normally you would say x is equal to plus or minus 20, but negative 20 doesn't make sense. We're talking about dimensions of a cube. You're not going to have negative 20 centimeters. So your answer here is that x is 20. And so again, because I'm looking for the x and y dimensions, you plug in x equal to 20 into the equation that you got here above. So that's the work you see here below. And so when you simplify, you get 15 minus 5, which gives you a value of 10. And so the dimensions are 20 centimeters and 10 centimeters. And we want to prove that this maximizes the volume of the box. So again, I'm going to use my second derivative test, which means I'm taking the derivative of v prime, and v double prime is negative 3/2 x. When I substitute 20 in for x, you get negative 3/2 times 20, and again, that's a negative value. Negative means concave down, which means I have a maximum. So the dimensions to maximize the volume of a box is x equal to 20 and y equal to 10. All right, so we're going to revisit the extreme value theorem in this problem, and it could have been done in all of the previous ones too. Remember, this extreme value theorem states that you have extreme values, maximums and minimums, as long as f is continuous on some closed interval from a to b. All right, so we came up with a function v that is certainly a continuous function. It's a polynomial function. So the trick here would be to determine what our boundaries would be. So we know that we're talking about dimensions, so they're not going to be negative. So your lower boundary could certainly be 0, although conceptually a dimension of 0 would mean that you don't have a shape at all. But it is possible to have a value of 0. It's just the cube would collapse or the box would collapse. There would be no box. But we would also need to know what our maximum value could be. And in order to determine the maximum value, I'm going to take this equation here and set it equal to 0 in order to see what my possible value, boundary value would be there. So I have 300 over x minus 1/4 x equals 0. This essentially creates a proportion. If you cross multiply, you get 1200 equals x squared. And if you take the square root of both sides, again, we're just going to look at the positive result, not the negative, again, because it's a dimension. So this is 20 root 3. So So you can say that V is continuous, is continuous on the closed interval from 0 to 20 root 3. So we already know our answers. Luckily, 20 falls within that interval, as it should be. And then if you think back to the way we did this when we were doing this with just graphs, remember we checked our values of our function at the beginning and at the end of the interval. So if here I have x values and here are my v of x values, when x is 0, v of x is 0. When x is 20, when x is 20, I have to do that here on the side. I didn't calculate that yet. Minus 1/4 20 cubed. I'm plugging it in here, by the way. So this is 6,000 minus 8,000 over 4. So it's 6,000 minus 2,000. So this has a value of 4,000. And at the other boundary, 20 root 3, it's also 0. So based on the extreme value theorem, you also see that when x is equal to 20, you have a maximum value. All right, so let's move on to another problem. Sorry about that. This one is based on the margins, a poster, and trying to minimize area. So here I have that the top and bottom of margins of a poster are each 6 centimeters, and the side margins are 4 centimeters. If the area of the printed material is 384 centimeters squared, find the dimensions of the poster with the smallest area. Okay, so again, I'm just going to change the color to make it easier to follow. Okay, I'll make it green. So here are our margins. I have a 6 centimeter margin at the top and bottom. So that's the border part of this poster. And then I have 4 centimeter margins on the sides. The inside of the poster, that's where the printed material is. We're told that that is 384 centimeters squared. So that is your constraint, that my inside of my poster has a constraint of 300, the area is 384. So I'm going to establish variables, which you see on the smaller poster. I have x and y here on the inside of the poster. And so x times y equals 384. All right, so we want to maximize the area of the big poster, including the margins. So we need to come up with an equation for that. Where we're also using our constraint variables. So if this dimension on the inside is x units, and I have 4 units on the left and right, that means that this entire dimension is x plus 8, because it's x plus 4 plus 4. Similarly, the longer side of the poster has y units on the inside, but then I have another 6 on the top and bottom. So y plus 6 gives me a dimension of y plus 12. So the area that you want to maximize is x plus 8 times y plus 12. So now we're back to doing what we did in all of the previous examples. We need to eliminate one of the variables, which means you take your constraint and solve for either x or y, and I decided to solve for y. So I have y equals 384 over x. That value, or that the 384 over x gets substituted into your formula that you want to maximize. So I get x plus y times 384 over x plus 12. Then you FOIL that out, and you get 384 plus 12x plus 3072 over x plus 96. So I'm here. I'm going to combine like terms and also rewrite the expression so that I can take the derivative easily. 384 plus 96 gives me 480. 12x comes down, and 3072 x to the negative 1 is the same as 3072 over x. So now I take the derivative. So the derivative becomes 12 minus 3072 x to the negative 2. We set that equal to 0. This again becomes a proportion. So you get 12 equals 3072 over x squared. Multiply both sides by x squared. 3072 divided by 12, well, that works out to be 256. Take the square root, it's a perfect square. X is equal to 16. And if x is equal to 16, then remember y was defined to be 384 over x. So you do that here, and you get that it's equal to 24. All right, so we want to prove that these values will allow us to minimize the area of the poster, because remember, that's what we were asked to do. Find the dimensions with the smallest areas. That's a minimum problem. Okay, so we have x equals 16, y equals 24. We're going to take a double prime. So here's a prime. A double prime becomes 6,144 x to the negative 3. When you substitute 16 in for a double prime, you get a positive result. And so positive means concave up. Concave up means that you have a minimum. Okay, but that doesn't quite answer the question. Your answers are not 16 and 24. Remember that the dimensions of the poster were x plus 8 and y plus 12. So we have to add 8 to x and add 12 to y. So your answers are here. X plus 8 is 16 plus 8, which is 24. Y plus 12 is 24 plus 12, which is 36. So the dimensions that will give you the smallest area possible are 24 centimeters and 36 centimeters. Okay, here's one more. This is regarding a rectangle inscribed inside of a circle. We want to find the dimensions of the rectangle of maximum area that can be inscribed in a circle of radius 6. Okay, so we have to use that information in order to come up with a constraint and an equation that we need to maximize that makes sense in terms of the information that you're told. So inscribed means that the rectangle's corners must touch the circle. If the radius is 6, then that radius will touch not only the circle, but it's also going to touch each of the 4 corners. So here's an example of what that would look like. But when I draw that radius, so remember this here is our radius, I just naturally can create this right triangle where x and y have a relationship with the sides of the square. And remember, we want to maximize the area, maximize the area of the rectangle. So if this side here is x, that means the entire side of the square is going to be 2x. And if that little side of the rectangle is y, then the entire side of the square is 2y. So you want to maximize length times width, which in this picture, it's 2x times 2y, and multiply that together, the formula that you want to maximize or take the derivative of is a equal to 4xy. Okay, so again, I want to eliminate one of the variables. So I'm going to go back to my constraint formula, and I'm going to solve it for y. And when you take this equation and solve it for y, you get y is equal to the square root of 36 minus x squared. Again, the negative square root would not make sense in a problem like this because we're talking about dimensions. Okay, so y equals to the square root of 36 minus x squared gets substituted into the formula that you want to maximize. So we put that here. I rewrote the radical as to the 1/2 power. So in this case, the derivative is not quite as simple as all the previous ones because here you have to use product rule. The work for product rule is here on the right. I'm going to put a green wiggly line around it. So f is 4x, f prime is 4. G is 36 minus x squared to the 1/2. To find g prime, you have to use chain rule. So we get 1/2 36 minus x squared to the negative 1/2 times negative 2x. So when you simplify the 1/2 and the negative 2, that just becomes negative x. And I rewrote the 36 minus x squared to the 1/2 and put it in the denominator with a positive exponent. All right, so we take that information and we put it inside of the product rule formula. So that's right here on the left. So I have f g prime, so it's 4x times negative x, 36 minus x squared to the 1/2, plus, and then I have f prime g, 4 times 36 minus x squared to the 1/2. So in the next line, I just rewrote the expressions in terms of their radicals, and I multiplied 4x and negative x. So I get negative 4x squared over the square root of 36 minus x squared, plus 4 times square root of 36 minus x squared. And we set that equal to 0. So when we set that equal to 0, it again becomes a proportion when you add the first term over to the right. So I get 4 square root of 36 minus x squared equals positive 4x squared over the square root of 36 minus x squared. And because this is a proportion, you can cross multiply. And when you do, when you multiply this radical over to the other, the radical goes away. So you end up with 4 times 36 minus x squared equals 4x squared. Then I distributed on the left, add 4x squared to the other side. So you're here, divide by 8. So you're here. And so you get that x is equal to the square root of 18. But 18 is the same as 9 times 2. So square root of 9 is 3. You get that x is 3 root 2. All right. So remember, this was a prime. It's not so easy to find a double prime. So we're just going to use the first derivative test to determine if 3 root 2 is actually a maximum dimension. By the way, y is also 3 root 2 when you plug it in. So in fact, if this works, your rectangle is actually a square. So we want to prove that these two dimensions, x and y, equal to 3 root 2, maximize the area of the rectangle inscribed in a, inscribed in a circle. All right, so I take a value less than 3 root 2, and 3 root 2 is about 4.24. So I picked 3. My test point is 3. I'm showing the work here. And I plug 3 into the first derivative. And if you work that all out, you get that it is a positive result. And positive means that the graph is, that the slope of the tangent line is going upward, meaning the function of a is going upward. And if you pick something greater than 3 root 2, and I picked 5, so I show the work here, you get a negative result, and so therefore it is going downward. And again, when you have a change in sign from positive to negative with your first derivative test, you can safely say that 3 root 2 is a maximum point. Okay, so those were your examples. You should try the example, for the homework for 4.7. So good luck.